So I'd like to get started, and if anyone comes in late, they don't need the first bit, which is just, me and setting the scene. So, a bit about me. I'm a chemical engineering graduate and have had too much experience in project engineering and management and project controls and risk management. And for the last 16 years or so have been involved in risk in various forms, in various sectors. So I started training people in the use of a tool called PERTmaster, which became Primavera Risk Analysis in 2003, and have been doing schedule, then cost and schedule, and integrated cost and schedule, and now parametric plus expected value and other ways of looking at risk. What I want to talk about today is, of course, as the title suggests, how we forecast time and cost contingencies for projects, and that's both large and small. So, very simply, we're going to take a look at, first of all, how a project estimated, look at a brief history of estimating contingency since about the last 70 years, and our experience, and address the question of what works best, which is hard to find in the literature. Okay, so first of all, how a project's estimated. So very simply, a detailed estimate's built from the bottom up, starting with the definition of the project scope. The base of estimate document, which should exist, documents the overall project scope, the assumptions and the exclusions, and should enable a reader who's experienced in this to understand and assess the estimate. So the basis of estimate includes all the known and quantifiable costs, the base estimate I should say, defined to be within scope. Then you have to add on the top a risk allowance, which is a representation of the costs additional to the base estimate due to two kinds of uncertainty. The first is the inherent uncertainty or risk that's certain to occur. It's just a question of how much is it in each case, and that's due to drivers of risk and inability to estimate exactly. The second kind is the kind that you'll find in a risk register, and that is what's called contingent risk, which is a risk that may or may not happen. So it has a probability that is less than 100%. And so there are two kinds of uncertainties in such risks. The first is whether they'll happen, how likely are they to happen, and secondly, if they happen, what kind of impact will they have on the project. So the project's developed in phases. That graphic there for risk allowance, contingency, is trying to hint that the risk allowance is an uncertain thing too, and it depends on how conservative you want to be, how big that allowance is. So projects are developed in phases, and that's because the primary driver of risk is scope definition, and we tend to define that progressively. And so we want to progressively do the work and spend the money enough to decide, does this business case stack up, and how much is the project going to cost, what's it going to earn the business, if it's a profitable kind of project, if it's a state-run thing, do the benefits justify the expenditure, and so on. And different industries have different terminology, but the common basis is that the successive stages define the scope more completely. So we have this progressive gateway process, and we're showing their different terminologies that are used. The top one is by a company called Independent Project Analysis Inc., and they call the process front-end loading, which is a peculiar term, but FEL 1 is at the very beginning, the concept phase, when you're assessing what is it that you're trying to do. The second, FEL 2, is where you're screening different approaches to the project and selecting the one you want to go with, and that's the pre-feasibility stage. And FEL 3 is where you're defining the project. It's the last stage before sanction or financial investment decision, and that is generally in some sectors called the feasibility study. And then you get into execution, where the die is cast and you've made your bed and you hope it's a comfortable one to lie in. So at the same time, there is a parallel process which the Association for Advancement of Cost Engineering calls its estimate classes. So FEL 1 corresponds to a Class 5 estimate, which is the most uncertain, through to just before sanction is Class 3, which interestingly AACE say is the most certain time or definition of the estimate you will get to, because as you execute there will be other uncertainties that come into the project. And that class structure determines what kind of uncertainty tolerance or band you're working in. Okay, so a person from AACE, John K. Holman, who's a life member, a life achievement member of the AACE, and was out here in 2018. He developed their total cost management framework and has developed a lot of thinking about risk and quantification of project risk. And he has provided some of the slides that I'm showing you now. So we have a representation of the uncertainty about an estimate, and that is a probability distribution, the blue curve, which shows you at the left-hand edge the most optimistic cost of the project to the right-hand edge, which is the pessimistic end. And the probability distribution goes through a mode, which is the peak probability. Then there's the mean, and hopefully to the left of that is the base estimate. And there's some information there for a mythical project showing how you would quantify the estimate with contingency. The P10, which is the low value, that's the 10% probability that you will be equal to or less than that amount. The P50, which is AACE's recommendation for the contingent amount for the project. But they also use the mean, and around most projects they are similar but not quite the same. The mean is usually a bit bigger than the P50, and a conservative value like the P90 is where you don't want to exceed, and sometimes some very conservative organisations use P90 and some may even use more. And I did for a time do some work in the Victorian Government Transport Department a few years ago, and they liked using P95 because they had recently recovered from the regional fast rail project, which went rather over any of their estimates. Okay, so the ideal situation is that as you develop the project, you're increasing the understanding of it. The blue curve is the FEL 1, the red one is the FEL 2, and the the green one is the FEL3, so that the contingent value for the project doesn't change. So you are narrowing the uncertainty, and the kurtosis or the peakiness of the curve is getting greater and narrower, so that by the time you're ready to sanction the project, you are confident of what that P50 or mean will be. However, the reality is more like this, that as more of the scope is defined, we get a creep of the estimated contingent value of the project, and Holman is quite agitated about the use of the term unknown unknowns. He doesn't like it at all, and he says that we should be able to get this right, and this sort of slippage shouldn't happen if you are doing a quality job of assessing the risk of the project. So poor control and change management practice and inappropriate project risk quantification lead to blowouts, and that's the sort of thing that you would see too often. So let's look at a brief history of forecasting project contingencies. There's a bit on this screen, but I'm trying to condense a bit of history into a short thing, and it's very hard to read that text, I accept. But first we're going to look at systematic assessment of what drives project cost outcomes created by parametric models using multilinear regression through analysis of completed projects. And this enables you to do a top-down assessment or forecast of the outcomes, time and money, for the project based on systemic risk factors such as scope definition, quality of leadership, organisation and project controls. So looking at this timeline, a gentleman named John Hackney started doing that in the mid-60s. In 1981, the US government, through the Department of Energy, commissioned the Rand Corporation to study the problem of cost blowouts, which were very large, and they were building nuclear power stations and plants, as well as other kinds of energy projects. And so they had 32 companies, I think it was, who contributed maybe 60 projects. And these were all studied using multilinear regression to find out what were the factors that drove the final outcome compared with the sanctioned time for the project and the sanctioned expenditure or budget. So that process was done for cost in 1981, for schedule in 86, and Rand went back to what they were most interested in, which was making money out of the US government for military work. And the data that came out of the Rand Corporation modelling, and that's a publicly available model because it was funded by the US government, but the data was bought by the leader of the Rand study, a gentleman named Edward Merrow, who became the owner and chief executive of Independent Project Analysis, or IPA Inc. And so since then, IPA has been the leading benchmarker of major projects around the world, particularly for profit ones, but not exclusively. And they come in at the request of the project owner, and they benchmark the work that's being done, particularly at the front end, to tell them where they're weak and where they're strong, mostly where they're weak, and help them to forecast what the outcome will be. In 1997, AACE defined the estimate classes, as I showed you in that timeline. And in 2016, Holman, who worked for IPA for 7 years and developed a lot of their metrics, published a book called Project Risk Quantification, a bit more about that later, and that drove renewed interest in the uptake of parametric modelling. In parallel with this, Monte Carlo simulation-based project cost risk analysis and schedule risk analysis were developed, and they were bottom-up modellings, and these replaced the discrete values for activity durations and cost line items with probability distributions. You then put that through a Monte Carlo simulation process where you would run maybe several thousand iterations of the project model and get a probability distribution for time and cost for the project. So early days, RAND were applying Monte Carlo to PERT for the US Air Force. In 1987 was when the first PC-based simulation tools for cost risk analysis were introduced, At Risk and Crystal Ball, which I'm sure a number of you would be aware of. And in the 1990s, project planning software combining with Monte Carlo simulation allowed schedule risk analysis to be widely used. In 2011, Dr. David Hewlett published a book called Integrated Cost Schedule Risk Analysis, which showed how to fully integrate cost risk analysis and schedule risk analysis so you could analyse them both simultaneously, including risk events. And in 2019, a practical method of combining parametric and integrated cost and schedule risk analysis methodologies was presented at the AACE conference. So how did we end up doing this stuff? So our company has gone through a number of iterations of ownership and so on, but the same team has been together for 13 years. And this is a bit about my career. In the 1980s, I was project manager for the first circulating fluid bed calciner plant that was built in Australia. It was a German technology, and it was built at QAL, which is still going and undergoing further changes. And that was a very interesting project. It saved a huge amount of energy compared with the old technology, which was like cement manufacture with a huge rotating cylinder and a big fire burning through it, and this wet sand going in at one end and coming out as calcined alumina at the other. And that was where I had my first exposure to critical path method planning and risk management in a serious way. In the 1990s, I got involved with a BHP project called Hot Briquetted Iron as a planning manager, and this was after BHP Iron Ore, which was an operating company. Their specialisation is digging dirt out of the ground and shipping it to their customers, and they were building a very complex plant to directly reduce iron ore to iron pellets, and they were partially reducing methane to, or natural gas, to CO and hydrogen to do that, and bubbling it up through fluid beds. So they embarked on this, and to meet the BHP board's threshold for return on investment of 15%, they cut $400 million out of the estimate, and they said that they would affect savings during the project. But poor project management and controls resulted in a 1-year delay and a 50% cost overrun. 1.6 billion turned to 2.4 billion. And BHP board sacked the BHP iron ore manager and the BHP minerals manager, who was his boss, for failing to keep the board informed. And a rescue team was sent in, and I was part of that team, and as planning manager we integrated 3 construction schedules and a commissioning schedule and established a valid critical path, which enabled us to actually forecast when the project would finish. And it also enabled us to show that the plant needed some modification to finish it in time. that was the most fun I think I can say I had in my professional career, in a way, apart from risk, of course. This project was killed partly by the financial crisis in 97, 98. The whole strategy was to sell flat products into the booming building market in Thailand and Malaysia and Indonesia, but there was a credit crisis, the currencies in those countries plummeted, all work stopped, and the price that they could get for their product plummeted. And the final straw was that the process itself killed the maintenance workers, because they had to keep chipping out the agglomerating iron ore pellets that were sticky. And in those agglomerations were trapped bubbles of CO and hydrogen, which, when combined with oxygen, made an explosive mixture. So the project has disappeared from Port Hedland. So on the left, you see the plant in construction. It was a huge thing. And on the right, you can see the upper photo is the moment when they blew it up. And the bottom one is picking up the scrap to be sent off to somewhere to be melted down. So nothing is there. If you drove past the Port Hedland golf course today, into Port Hedland, you would, on the left, have seen this project. There is nothing there. In the 2000s, we got involved in schedule risk analysis, and that was a most interesting and satisfying experience. And that was about forecasting the end of projects when they were under construction. And we were able to achieve quite significant accuracies in the forecasting, but it was an iterative process. And that convinced me that schedule risk analysis was a really useful thing for projects. We then went on in the period roughly in the teens, 2009 to 2015, doing integrated cost and schedule risk analyses for the Santos Gladstone LNG project. And that also was quite successful. The schedule side of it was easy to verify. Cost is a bit harder to get out of companies. They don't really want to make public how much a project actually cost them. But in general terms, it was a very interesting and worthwhile exercise. Firstly, for the project itself, up to financial investment decision at the beginning of 2011. And then on the upstream side, we did a whole series of feed analyses of projects that were worth up to 1.3 billion. In the same period, we did work for an oil and gas explorer, Talisman Energy, Canadian company, now owned by Repsol, Spanish company. They were exploring for gas and condensate in Western Papua, and that is a nightmare place to get to because there's no roads and you have to fly everything in, people, materials, equipment, by helicopter, and it's jungle, and the natives are not always friendly. We suggested, after they told us that they had missed their targets for the first 3 years, and they were doing linear planning and estimating, and we suggested doing cost and schedule risk analysis because it was a high risk and high cost environment, so they needed to do a probabilistic forecast of how long their work would take and how much it would cost. So we managed to get some real data out of some of the work they did, and the left-hand table shows part of the building blocks of the exploration process. It was treated as a lean manufacturing process where you did seismic surveys, analysis, which was more like a black box. Then you did the analysis would tell you where to drill. You would then have to do the site preparation. That's a project. Do the drilling. That's another project. Or there's the rig move in and the drilling. All of it, each could be chained together with generic integrated cost and schedule risk analyses with a suite of risk events that had been developed for each of those stages. So the rig move, they did without risking it, that is, without doing a risk modelling. The drilling, they did as a risked analysis, and you can see the contrast with two different wells between the non-risk analysed model, which was just linear programming, and the probabilistic forecasting, which was either within the budget or just slightly over. So that was very heartening, and the manager with whom we worked on that, who became the country manager for Talisman, told us that this work had restored their credibility with their head office because they were able to make forecasts they actually met, which was good. And this gives you an idea of just how difficult that terrain is. 10 metres of rain in 9 months every year, 10,000 millimetres of rain. And when it wasn't raining, the cloud cover was often so low that you couldn't fly. So you really had to model the time in a day that you could fly a helicopter down to the quarter of an hour, which we did. And that was good. Now, there are problems with cost risk analysis and therefore integrated cost schedule risk analysis, and that is at the high end, this bottom-up process does not replicate the known experience of high cost outcomes, particularly for large projects, despite careful application of correlation, which is linking things that are related to each other. Monte Carlo simulation has a base assumption that every uncertain element is completely independent of every other one. And you have to tell the modelling software, whatever it is, how related various elements or groups of elements are. And that's a very important part of doing valid modelling. So we recognised that we were not getting full compliance with AAC's recommended practice for contingency estimating. There were general principles, and one of those is that the method you use employs empiricism, and that means explicitly analysing past performance in projects and assigning systemic risk, I should say, through multilinear regression, otherwise known as parametric quantification or modelling. So the more indirect approaches to incorporating past performance identified by that recommended practice, that is, instead of putting in directly past performance in projects, you could use lessons learned, do benchmarking, or validating the analysis results against historical data. Our methodology, as for most practitioners, was not formally including that stuff because the clients, by and large, did not have that information, and they still don't. Very few organisations systematically collect their project information and store it and organise it. Bechtel is one company that has in the past done it. I'm not completely convinced they're still doing it, but they required their clients to pay for the post-completion compilation of all the performance indices and lessons learned and so on. So real outcomes were not realistically reflected in cost contingency assessments, as indicated in the next graphic. So the red is what we think we're doing, and the blue is what is actually happening. And that is particularly bad in the pessimistic end of the forecasting. So what can be done about it? It does point to the failure to represent the long pessimistic tail of actual project cost outcomes realistically. And there's even a little bump around P90 where projects have gone completely feral and go into a chaotic state. And Holman's done some analysis about that, and he looked at chaos theory and complexity theory, decided the maths was terrible and came up with a traffic light system, which would appeal to engineers really. And so based on certain metrics, he forecasts how likely it is that any given project will fall into a chaotic state. And I've been on several of those where hundreds of thousands of man-hours extra have been consumed. Okay, so we wanted to do something. Along comes Holman's book, Project Risk Quantification, 2016, and it gives you a different view of project risk. And it says, let's look at how to quantify risk by the way we assess it. So rather than looking at inherent risk, as we looked at before, and contingent risk, let's look at the risk that dominates in projects of all kinds, which is systemic risk. That is the risk due to the project delivery system, which comprises the organisation's structure and their culture, the leadership, the project team, the processes and the capabilities. So there is also the scope definition, as I mentioned earlier. That's the big driver of uncertainty, but after that, it's those other ones I've just listed. So he advocates a hybrid methodology where you first of all assess systemic risk using a parametric model, which you configure by conducting a workshop with the project and the organisation to identify how strong or weak is that project delivery system, how well is the scope defined, is there new technology, and how complex is the project, how big it is. These are all risk factors. And so that goes into the parametric model, and the second part of his methodology is to use something called expected value, which is simply the probability of a risk by the impact. And you would have all seen that in a risk matrix heat map. A key point of this methodology is you don't have to have your own project performance. You can, in fact, draw on generic information that is available to use this method. And that is a really liberating thing. So you do not have to spend the necessary years to accumulate all that stuff to get started in it. It does help if you do it because you'll get better at it and you'll get much better at it. But that's all to do with general project management improvement too, lessons learned, you know, sharpening the saw and all that. So the thing that struck me about this was we could incorporate that systemic risk into an integrated cost and schedule risk analysis and map the major project-specific risks not covered by the systemic risk into our model in the right places in the schedule. And that takes care of float and uncertainty from a schedule point of view, as well as the cost. So that is a more sophisticated approach than the expected value method, which doesn't require a schedule. So I delivered a paper in 2017 in which I added in the systemic risk from Holman's methodology, parametric modelling, using risk factors to apply it in cost and schedule over the whole project. But I was accused of double dipping because the systemic risk includes the inherent risk. And so I had to think about that again. And while I was attending, around the time I attended a course by Holman, I became convinced that we could work out a net systemic risk by subtracting the base estimate and schedule model, integrated cost and schedule risk analysis, uncertainty curve, from the systemic risk curves generated from the parametric modelling. And we do that subtraction by Monte Carlo modelling. So that's described in detail in a paper that will shortly be available on our website, which I delivered in June at the AACE conference in New Orleans. So the methodology's been successfully implemented with clients since mid-2018. So the common elements of CPM-based ICSRA are assess the inherent risk by developing the duration and cost ranges, and map the treated risk events into the model in a similar way to running an expected value process. So the parametric modelling is a top-down process, as I said, which configures the coefficients on the parametric modelling of systemic risk, and that gives us our distribution. And that expected value method enables us to get a quick solution to the overall question of time and cost contingency without needing a schedule. You only need the scheduled duration for execution of the project and the budget estimate for the base estimate for the execution phase of the project. And the P plus IRA methodology maps it into the project. So the question that we need to end up with is, what methodology works best? IPA reported on schedule risk analysis versus cost risk analysis. This is Ed Merrow in a book called Industrial Mega Projects in 2012. It's a very candid view of what works and what doesn't in managing large projects over $1 billion. So he said that schedule risk analysis is useful, but cost risk analysis is worse than useless. And the only uncertainty I have about that is he used a slightly different terminology, and he could be talking about cost range analysis with no risks mapped into it. But he shows on a graph, and that's it, that when you do a Monte Carlo cost risk analysis, the data they've got from all the projects they've reviewed, thousands of them, is that they flatline against the front-end loading thoroughness. So the bottom of that is front-end loading index. On the left, it's best, and on the right, it's worst. And the contingency in an estimate without Monte Carlo is the one with a very shallow increase in slope. The horizontal line that's nearly horizontal is the contingency in estimates with Monte Carlo, and the actual cost deviation is the straight line he's drawn that it has a steep slope, and he gives you the residual uncertainty for these things in the little boxes. So he's quite rigorous with stats. So he, in contrast, says schedule risk analysis results in a 27% decrease in the amount of execution schedule slippage, and therefore that means a 27% decrease in the increase in time-dependent costs, which is a major source of project cost blowout. So this plays out in lower project startup failure and better operability, apart from better cost contingency accuracy. So parametric modelling benefits. Incorporating parametric modelling ensures contingency assessments are based on past performance and avoid optimism bias. Naturally, the team on a project want the project to go ahead because they keep working. And it's a difficult problem, and another problem is narrow distributions when you get ranges from project teams on durations and also cost. They generally cannot estimate the magnitude realistically of how much stuff will change. So parametric modelling produces log normal distributions of cost and schedule outcomes based on strengths and weaknesses of the project delivery system. And earned value Monte Carlo simulation adds the project-specific risk events to produce an overall execution phase cost and schedule distributions for contingency setting. So that's an example of the systemic cost contingency distribution, and there's a schedule one, both produced from parametric modelling, and as I said, we subtract from those the base IRA cost and schedule distributions, and that gives us net systemic risk factors which we apply overall to the project schedule and estimate for Monte Carlo modelling. So when do we use these methodologies? Well, the obvious thing is where we don't have a schedule. So in the early stages of a project, you can use parametric plus expected value for concept and for even pre-fees. And I've done a number of those using this methodology. So it's a good solution for projects that are small or in their early phase of development. You can get the inputs, do the workshop, and within a week provide the outputs to the client. So we've done that on 2 mining tailings dam projects in pre-feasibility stage and 1 mining tailings dam project at full feasibility study stage, with a parallel schedule risk analysis where we were providing them with more than just the overall schedule contingency, but of the intermediate milestones and portions of the scope that you can't get out of P plus EV. 1 complete metallurgical coal mine, pre-feasibility study, and again a parallel SRA was conducted, and a medium-scale highway relocation which is queued to be done early in the new year. The overall schedule contingencies from the SRAs were in good agreement with the P plus EV contingencies, and that answers a serious concern by the scheduling and the bottom-up CPM people who were worried that you couldn't make a realistic schedule forecast without a schedule. When do you use P plus IRA? Well, for the major projects, which are so big, there's a lot of money in them, and also just prior to financial investment decision. So you need a good quality schedule and significant time and effort. Getting the good quality schedule is no easy task, and it requires often quite a bit of iterative feedback to the project team to make a schedule technically acceptable. So with the inclusion of schedule risk analysis overlaid with costs, we can optimise the time-dependent costs and schedule uncertainty, and it's also justifiable for medium-scale projects just prior to funding, and as I say, for major and complex projects at the end of FS and PFS if a good schedule is available. We've used this methodology on a complex pharmaceutical industry project. We've done that twice, and a minerals processing mega project, which we also did twice. They wanted it updated with further information. We've also done it on a medium scale natural gas peak shaving plant expansion that was dependent on the commercial viability of the expansion to proceed. In each case, we prepared the analyses, and in each case, the P plus IRA produced significantly wider spreads than the old style IRA on its own. And in each case, the clients, who were multinational corporations and were initially quite nervous about using parametrics with integrated cost and schedule, they wanted to go with integrated cost and schedule because that's what they were used to. And in each case, they said, no, we'll take the P plus IRA, thanks, because it gave them a much more realistic outcome than they got from IRA alone, or ICSRA. Okay, conclusions. CPM-based ICSRA, a bottom-up Monte Carlo simulation methodology, has been combined with parametric modelling, a top-down configuration methodology derived from more than 50 years of industry-based research on the drivers of cost and time outcomes of projects. The parametric plus IRA methodology enables risk optimisation and realistic cost and schedule contingency forecasting to be combined. For earlier stages where you haven't got a suitable schedule or it's too small, P plus EV is quicker and costs less and does a good job overall. So if you've got a good schedule available for a small project, you can also do SRA in parallel. It's more cost effective than doing a full ICSRA with parametric. Okay, so for more information, you can look at John Holman's website, which is validest.com. Our website's riskinteg.com. You can go to the AACE international website to join up, and you can also, for a modest fee, get their recommended practices, which are industry proven. And Australian Cost Engineering Society, costengineer.org.au. So, any questions? Right, so either you fell asleep or your brains are full. I'm not sure which. Yes, Michael.
When you turn up on site, quite common, I imagine,
Here's a microphone, Michael.
Thank you. When you turn up on site, I guess it'd be quite common that there would be not one schedule, but multiple schedules, you know, as a part of their schedule control system. What do you do in that case? Do you take all that, produce another good quality schedule? Is that the way to go? Or?
Okay, so good question. On a major project, you would expect there'd be an integrated control schedule, level 3 probably. There should be in existence, otherwise how can the project director know what's going on? You need an overall schedule that ties everything together. If you don't have it, or if it's too big, and we've struck jobs with 10,000 activities or more, we say either we have to summarise it or you do. So come back to us when you're ready if you want to do it as a competitive tender, or get us involved and we'll summarise it for you, which we have done. Any more? There were some other questions that have been stifled. I don't mind if you ask dumb questions, that's absolutely fine. You could ask me something absolutely fundamental and I'm happy to answer it. Doug?
Colin, just drawing a parallel between this and the previous lecture, the comment you made about the schedule range analysis being effective, do you think that has some alignment with critical chain philosophy, where if you take the time to look at variability in the schedule and understand it, that it gives you an advantage?
They're slightly different perspectives, but I'm a fan of critical chain. I think it's a really good idea to accumulate buffers, and it's a more efficient way. It'll drive better outcomes. You know, there's Parkinson's law that time or work expands to fill the time available, and what you're doing with critical chain is trying to drive as early a outcome of the project completion as you can, while still being realistic about how much time you're going to allow. We haven't used a critical chain schedule as an input, but I don't see why you can't. Yeah, inherently, you can do it, and I've seen where people are using exclusively risk factors applied over the whole project. No ranging of the individual activities. We're agnostic about that. We don't mind. Yes, sir.
How do you expect these methodologies would be applicable to IT projects?
IT projects, and I've worked on IT projects, are no different from any other projects except for the resistance of the IT world to the strictures and the discipline of project controls. So IT people say, we are creative people. How dare you impose these constraints on us? But otherwise, they're just like any other project. And I can tell you, as you may well know, some of the most egregious overruns in projects have happened in IT. I can rattle off Queensland Health, comes to mind, and there are others that would rank. A lot of defence projects are driven by IT, and as a colleague of mine who's in that world says, usually the longest pole in the tent is the software development. So the Joint Strike Fighter was left with a technical debt of 20 million lines of code or something, and it was going to take a very long time to get all that sorted out. So Parametric is a good methodology for the IT world. Anyone else? Well, thank you very much for coming and your attention.